Dear students, hello! The topic of this lecture is bounding blending. A blending operation in shape modeling generates smooth transition between two surfaces. Such operations are usually used in computer-aided design for modeling fillets and chamfers. Bounding blendings means controlled blending operations. This lecture is based on this article. The content of this lecture is following. First of all, we'll consider the blending set operations defined using R functions and displacement functions with the localized area of influence. Next items will be the shape and location of the blend defined by the control points on the surfaces of two solids, or by an additional bounding solid. And finally, the blend properties and applications will be discussed. Blended versions of set theoretic operations, intersection, union, and difference, on solids approximate exact results of these operations by rounding sharp edges and vertices. As example, in the case of blending union of two disconnected solids, one resulting solid with a smooth surface with material addition can be generated. In the case intersection of two disconnected solids, one resulting solid with material subtraction is generated. For controlled blending operations, there are following requirements: tangency of the blend surface with the initial surfaces, automatic clipping of unwanted parts of the blending surface, blending definition of the basic set theoretic operations, support of added and subtracted material blends, intuitive control of the blend shape and position. You can see the list of existing approaches for blending operations. Its approximation of min and max operations, analytical blends with truncation, controlled blends, blends based on R functions. The last one we consider in more detail. The contour lines of the intersection of half planes are shown on this slide. The intersection is described by R function. This function has a curve with a sharp vertex, both line of the slide, as a zero-value isocontour of function f. Other contour lines are smooth in the entire domain. This property brings the idea that some displacement of the exact R function can result in blending effect between the lines, as shown in this picture, or primitives. The definition of the blend set theoretic operation is shown on this slide, where is an R function corresponding of the type of the operation. The arguments of the operation f1 and f2 are defining function of two initial solids or primitives, and d of f1 and f2 is a Gaussian type displacement function. The following expression for the displacement function can be used, where a0, a1, and a2 are parameters controlling the shape of the blend. The proposed definition is suitable for blending union, intersection, and difference, allows for generating added and subtracted material, symmetric and asymmetric blends. On this slide you can see the advantage of R functions as a set theoretic operations in comparison with min-max functions. When we apply blending operation to the object produced by min-max operation, we can get such artifacts as unwanted edges, middle picture on the slide, while the R function gives good result, right picture on the slide. By changing parameters a1 and a2, we can get different results of the operation and control addition or removal of material. You can see on this slide the example of intersection operation with different values of parameters a1 and a2. This is an example of the blending union operation. There are following problems with blending. Firstly, blend is global, never touch initial surfaces. Secondly, displacement function is not limited by some distance or other constraints. Thirdly, difficult to control the overall shape. On the previous slide, we consider the uncontrolled blending operation. To get a controlled blending operation, we need to change the displacement function with conditions shown on the slide. It's called bounded displacement function, and the operation is called bounded blending. A plot of the desired displacement function is shown in this figure. This is one of the possible expressions describe such plot. Here R is a generalized distance which is constructed using defined function of the initial solids. We discuss here the first and possibly the simplest method of the blend localization, bounded blending using control points. The idea is to place one control point on the surface of each initial solid and to require that blend exists only between these control points. The control points are supposed to be relatively close to the edge resulting from the pure set theoretic operations, and it should be intuitively obvious what area is designed for blending. To satisfy such requirements, the displacement function should become zero at the control points with the maximal value or on near the edge. Here you can see the following properties of this function. These properties mean that displacement function takes maximal value at the intersection points of two surfaces, where f1 and f2 are equal to 0, and becomes 0 at control points p1 and p2. The bounded blending union operation of two rectangles with control points is illustrated by this figure. Two control points are placed on the corresponding boundaries of the rectangles. The expected bounded blend appears between the control points at the upper left part of the shape. However, the rectangles are blended also in the lower right part of the shape, which can be unexpected or unwanted. This example unveils the global character of the blend with control points. The introduction of an additional bounding solid can bring real local character to the blend. It's required that the blending surface exists only inside the bounding solid. The upper part of the figure shows two solids to be blended, defined by the functions f1 and f2, and a bounding solid, defined by the function f3. The plot of the displacement function is shown in this figure. Let's consider bounding solid requirements. First of all, the zero value of the displacement function should be outside the bounding solid. Secondly, the maximal value of the displacement function should be near the intersection point of two initial surfaces. Also, the zero value of the generalized distance function r should be at the intersection points of two initial surfaces. And finally, the value 1 of the function r should be outside the bounding solid. The following definition for the generalized distance function satisfies the above requirements. Now let's consider bounded blending properties and applications. The use of a bounding solid allows the user to select a single feature, vertex or edge, of the constructed solid for blending. In this figure, an example of union of two rectangular solids in two-dimensional is presented. A two-dimensional disk is used as a solid bounding the blend in the area near a single vertex, figure A. The pure union operation is replaced by the bounding blending. The expected bounding blend appears inside the bounding disk in the upper left part of the shape, in figure B. However, in comparison, bounding blending using control points, no blending appears in the lower right part of the shape. This example illustrates the local character of the blending with a bounding solid. The shape and position of the blend is controlled by its parameters and by the position and shape of the bounding solid. On this slide you can see the influence of the parameters on the resulting form. The absolute value of A1 defines the total displacement of the blending surface from the two initial surfaces. AO equals 0 means pure set theoretic operation. A positive A0 value yields added material blend, and a negative AO value gives subtracted material blend. Values of A1 and A2 greater than 0 are proportional to the distance between the blending surface and the original surfaces defined by F1 and F2 respectively. Symmetric blends and asymmetric blends can be generated by changing these parameters. Parameter A3 controls the influence of the bounding solid on the overall blend shape. It is proportional to the distance of the blend surface to the surface of the bounding solid. Control of the blend shape and position in 3D is illustrated on this slide. Here is an example of bounding blending operation. You can control the place and size of blended area by bounding solid, the third transparent shape on this slide. The definition of the bounding solid by a single function allows for unusual operations, such as multiple blending. Multiple blending controlled by a bounding solid consisted of 6 disconnecting components is shown on this slide. Here, blending intersection of two planar half planes is bounded by an elliptical solid, which overlaps only with a part of the intersection H. As a result, we can observe the transition of the subtracted material blend to the sharp edge at the point of intersection between the edge and the surface of the bounding ellipsoid. This example where we can use blend-on-blend operations. The proposed bounding blending operations can replace pure set theoretic operations in the construction of a solid without rebuilding the entire construction tree data structure. The example you can see on this slide. Initially, the model is constructed using set theoretic operations with two unwanted sharp edges in the area of the spout and at the top of the pod body. After applying bounded blending with complex bounding solid, we got smooth edges on the pod. In addition, bounding blending operations have 3 solids as their arguments, and hence require 3 array nodes in the construction tree.